January 17th, 1940. Paterson, New Jersey. The snow fell in soft sheets across the refinery yard. In the pale winter light, the towers of Standard Oil's catalytic cracking unit stood like cathedral spires against a slate sky, their steel surfaces slick with ice. Inside the control room, a handful of engineers huddled around a single glass beaker containing a clear, volatile liquid. It looked like water. It smelled like the future. When they poured a measure into the test engine and turned the ignition, the roar that followed was not merely mechanical light, was the sound of history pivoting on an invisible axis. This was 100-Octane Aviation gasoline, and in that frozen morning, as the engine screamed at altitudes no American aircraft had reliably reached before, no one in that room could have known. They were holding the weapon that would decide the war that had not yet reached them, across the Atlantic. The skies above Europe were already darkening. The Luftwaffe's Messerschmitt Bf-19s carved through the clouds on 87-octane fuel. Their Daimler-Benz engines, tuned to a deadly precision that had made them masters of the air in Poland and would soon dominate France. In Tokyo, engineers at Mitsubishi pored over designs for the Zero fighter, a machine so light, so maneuverable, that it would become legend in the Pacific, running on fuel refined to roughly 92 octane. These were the standards of the world's most advanced military aviation programs. These were the benchmarks of air superiority. And on that January morning in New Jersey, a country that had no high-octane aviation fuel industry, no strategic reserves, no tested production methods for such a substance, had just created something that would render all of those standards obsolete. But this moment did not arrive from ambition alone. It arrived from desperation. The crisis no one saw coming in the winter of 1940. The United States was not yet at war, but its military leadership was not blind. Army Air Corps officers, still small in number and often dismissed by the battleship admirals who dominated military thinking, had been watching the war in Europe with growing alarm. The reports from France, from the Low Countries, from the burning skies over Britain, all told the same story. Air power was no longer a novelty. It was the deciding factor. Whoever controlled the skies controlled the battlefield, controlled the seas, controlled the future. And control of the skies depended on one thing, above all else: engine performance. American military aviation in 1940 was a study in inadequacy. The standard fighter of the Army Air Corps was the Curtiss P-40 Warhawk, a sturdy aircraft but one that struggled at high altitudes and could not match the climb rates or speed of its European counterparts. The reason was not design alone, it was fuel. American aviation gasoline, even the best grades available, hovered around 87 to 91 octane. This was sufficient for commercial aviation, for the mail planes and passenger carriers that crisscrossed the continent. It was not sufficient for war. Octane rating measures a fuel's resistance to knocking the premature detonation of fuel in an engine's cylinders. That causes loss of power, engine damage, and catastrophic failure at high stress. In an aircraft engine pushed to its limits, climbing steeply, dogfighting at thin altitudes, every octane point mattered. Higher octane allowed higher compression ratios, higher boost pressures from superchargers, higher power output without destroying the engine. The German Bf-109, running on 87-octane B for fuel, could generate 1,100 horsepower in its Daimler-Benz DB 601 engine. The British Supermarine Spitfire, using 100-octane fuel developed in desperation after Dunkirk, could push its Rolls-Royce Merlin engine to 1,300 horsepower and beyond. The difference was survival. The difference was victory. And America, the industrial giant, the land of oil derricks and refineries stretching from Texas to California, did not produce a single gallon of 100-octane aviation fuel for military use. This was not an accident. It was economics. refining high-octane. Fuel required a radically different process than the thermal cracking methods used to produce standard gasoline. It required catalytic cracking, a complex chemical process using catalysts aluminum chloride, later silica-alumina compounds, to break down heavy hydrocarbons into lighter, more volatile molecules with higher octane ratings. The equipment was expensive. The process was finicky, dangerous, prone to failures. And there was no market. Commercial airlines did not need it. The military had not demanded it. So the oil companies, rational actors in a peacetime economy, had not built it. But by the winter of 1939, with Poland crushed and France bracing for the inevitable German onslaught, rationality took on a different meaning. The Army Air Corps, in quiet consultations with the Navy's Bureau of Aeronautics, approached the major oil companies with an urgent request: develop 100-octane fuel, and develop it now. Not for a distant future war, for the war that was already consuming the world. The gamble in the refinery styled. Oil of New Jersey, later Exxon, was not the only company approached, but it was the one that moved fastest. The reasons were partly technical, partly political. Standard Oil had been experimenting with catalytic cracking since the early 1930s, not for aviation fuel but to improve automobile gasoline yields. A French engineer named Eugene Haudery had developed a catalytic cracking process that Standard Oil licensed, and by 1938, a small pilot plant was operating in Paterson, New Jersey. It was designed to produce high-octane components for automotive fuel. But the chemistry, the engineers realized, could be adapted if they pushed the process harder, controlled the temperature more precisely, selected the right feeds. They could produce iso-octane and other high-octane hydrocarbons suitable for aviation. The problem was scale. A pilot plant producing a few hundred gallons a day was one thing. A production facility capable of supplying the military thousands, then tens of thousands, then hundreds of thousands of gallons a day was another. And there was no guarantee it would work. Catalytic cracking was temperamental. Catalysts degenerated quickly, clogged with carbon, lost effectiveness. The process required constant regeneration, precise temperature control, sophisticated engineering. A failure at scale could mean millions of dollars lost, reputations destroyed, and worst of all, the military left without the fuel it desperately needed. But the engineers at Standard Oil, along with their counterparts at Shell, Texaco, and other companies, understood something that transcended quarterly earnings. If Britain fell in early 1940, that seemed a very real possibility, would stand alone against the Axis powers. And if America stood alone, its aircraft would face the Luftwaffe, the Regia Aeronautica, eventually the Imperial Japanese Navy Air Service. Without 100-octane fuel, they would face them at a disadvantage that no amount of courage or manufacturing capacity could overcome. So they built it. In Paterson, in Baton Rouge, in Los Angeles, refinery complexes expanded with a speed that defied the peacetime bureaucracy. Standard Oil invested over $130 million, equivalent to nearly $3 billion, today into catalytic cracking facilities before a single military contract was guaranteed. Shell Oil built a massive plant in Martinez, California. The Texas company, later Texaco, constructed units in Port Arthur. By the summer of 1940, as the Battle of Britain raged and the fate of Western civilization hung on the performance of a few hundred Spitfire and Hurricane pilots, American refineries began producing 100-octane aviation gasoline in quantities large enough to matter. The British, facing annihilation, were the first to receive it. Shipments of American 100-octane fuel crossed the Atlantic in convoys, running the gauntlet of U-boats to reach RAF airfields in southern England. When that fuel entered the tanks of Spitfires and Hurricanes, the pilots noticed immediately. The engines ran smoother at high boost. They could climb faster, fight longer, pushed their aircraft harder without the sickening knock that signaled imminent failure. RAF records from late 1940 show a marked increase in engine performance and reliability once 100-octane fuel became standard. It was not the only factor in Britain's survival radar tactics. The courage of the pilots themselves all mattered, but it was a factor that could not be ignored. Every additional 100 feet of altitude, every extra 10 miles per hour, every minute longer an engine could sustain emergency power, translated into lives saved and bombers shot down by December 1941. When Japanese aircraft struck Pearl Harbor and America entered the war it had been preparing for, the transformation was complete. The United States was producing over 40 million gallons of 100-octane aviation fuel per year. By 1943, that number would exceed 600 million gallons annually. The infrastructure, the supply chains, the technical expertise that had seemed impossible in 1939 had become routine. Tanker trucks and rail cars moved the fuel from refineries to airfields across the country and around the world. In Britain, in North Africa, in the Pacific Islands, in China, wherever American aircraft flew, 100-octane fuel flowed. The impact on aircraft design was immediate and profound. Engineers, freed from the constraint of octane fuel, redesigned engines for higher compression ratios and supercharger boost pressures. The Pratt & Whitney R2800 double wasp engine, which powered the Republic P-47 Thunderbolt, the Chancefort F4U Corsair, and the Grumman F6F Hellcat, was designed from the outset to run on 100-octane fuel. It produced 2,000 horsepower reliably, a figure that would have been impossible with 87-octane. The Allison V1710 engine in the P38 Lightning, the Packard-Belt Merlin in the P51 Mustang all were optimized for 100-octane performance. These were not incremental improvements. They were generational leaps. The Japanese encountered this reality in blood and fire. In early 1942, during the battles of the Coral Sea and Midway, American carrier pilots flying F-4F Wildcats faced the legendary Mitsubishi A6M0. On paper, the Zero was superior in almost every measure: lighter, more maneuverable, longer range, faster climb. Japanese pilots, veterans of China and the early Pacific campaigns, were among the most skilled in the world. But the Wildcat, though heavier and less agile, had one critical advantage: its engine, running on 100-octane fuel, could sustain full emergency power for longer periods without damage. American pilots learned to avoid turning dogfights, where the Zero's agility was decisive, and instead used high-speed slashing attacks, diving from altitude, firing, and climbing away using raw engine power the Zero could not match. It was not elegant, but it worked. By 1943, when the F6F, Hellcat, and F4U Corsair entered service, the imbalance became insurmountable. The Hellcat's R2800 engine, gulping 100-octane fuel, produced 2,000 horsepower, and could push the heavy fighter to speeds and climb rates the Zero could not approach. Japanese pilots, still flying Zeros with engines designed for 92-octane fuel and unable to produce high-octane fuel in sufficient quantities due to limited refining capacity and resource shortages, found themselves outmatched. The kill ratios told the story. In 1942, American and Japanese pilots traded losses roughly evenly. By 1944, American pilots were achieving kill ratios of 10-1, sometimes higher. Superior tactics, superior training, and superior numbers all contributed. But at the heart of that superiority was an engine that could use every ounce of power its designers intended, without hesitation, without fear of failure, because the fuel allowed it. The Germans faced the same calculus in the skies over Europe. The Luftwaffe, which had entered the war with qualitative superiority in aircraft and pilot training, found that advantage eroding as American and British aircraft, fueled by 100-Octane, matched and then exceeded their performance. The P-47 Thunderbolt, derided by some American pilots as too big and heavy, became a terror in the hands of pilots who understood its strengths. At altitude, boosted by its turbo supercharger and 100-octane fuel, the P-47 could dive faster than anything the Luftwaffe fielded, could sustain high speeds longer, could absorb damage that would down lighter aircraft. German pilots learned to fear the sound of its 8.50 caliber machine guns, learned to recognize the silhouette of its bulky fuselage, learned that engaging it in a diving fight was suicide. The P-51 Mustang, perhaps the most iconic American fighter of the war, owed its dominance to two factors: a brilliant airframe design and the Packard Merlin engine running on 100-octane fuel. The Mustang could escort bombers to Berlin and back, a mission profile that earlier fighters could not sustain. Its engine, sipping 100-octane through carefully managed fuel systems, provided the range and reliability to make that mission routine. When Mustangs appeared over Germany in 1944, flying top cover for bomber streams, the strategic calculus of the air war shifted irrevocably. The Luftwaffe, forced to engage or watch its homeland be destroyed, bled its remaining veteran pilots in battles. They could no longer win, the symbolism of abundance. There was a single object that symbolized the industrial and ideological gulf between America and its enemies. It was not the aircraft themselves, not the guns or bombs, but the fuel. 100-octane gasoline was the liquid embodiment of American abundance. It represented an economy so vast, so productive, that it could afford to over-engineer, to build redundancy, to pursue perfection, not because it was necessary for survival, but because it was possible. To a Japanese logistics officer, staring at dwindling reserves of 92-octane fuel and no capacity to produce more, the knowledge that American pilots had access to unlimited quantities of superior fuel must have seemed almost incomprehensible. To a German engineer, watching Luftwaffe fighters struggle to match the performance of American aircraft despite equivalent or superior designs, the realization that the gap was not engineering but resource specifically must have been maddening. The contrast ran deeper than performance metrics. It touched on the philosophies of war that each nation embraced. Japanese military doctrine emphasized spirit, discipline, the willingness of the individual warrior to sacrifice everything for victory. The Zero fighter embodied this. Light, fragile, lacking armor or self-sealing fuel tanks, it traded protection for performance, gambling that superior agility and pilot skill would overcome material deficiencies. It was a philosophy born of necessity. Japan lacked the industrial base to produce heavily armored fighters in large numbers, but it was also a reflection of cultural values that prized austerity and sacrifice. Germany, more industrialized than Japan but still resource-constrained, pursued technological sophistication as a force multiplier. German engineers designed aircraft that were often superior in specific performance envelopes: the Focke-Wulf FW-190's roll rate, the Messerschmitt Me 262 jet speed, but they did so within constraints imposed by fuel shortages, material shortages, and the grinding attrition of a multi-front war. German aviation fuel production never approached the scale or quality of American output. Even late-war synthetic fuel programs, using coal liquefaction, could not produce 100-octane equivalents in meaningful quantities. The result was aircraft that, on paper, matched or exceeded Allied designs, but in practice operated under limitations their pilots could never fully escape. America, by contrast, fought a war of material overwhelming. The philosophy was simple: build more, build better, and supply it all so abundantly that logistical concerns became secondary. 100-octane fuel was not rationed to frontline fighters alone. It was available for training aircraft, for transport planes, for any mission where performance mattered. American pilots trained on the same fuel they would use in combat, developing an intuitive understanding of their aircraft's capabilities without the need to compensate for inferior fuel. When they reached the front, they flew knowing that every ounce of performance the engineers had designed into their aircraft was available to them. No compromises. No asterisks. This abundance had psychological effects that are difficult to quantify but impossible to ignore. Japanese pilots, by 1944, knew they were flying obsolete aircraft with inadequate fuel against an enemy that seemed to have infinite resources. The knowledge bred a fatalism that no amount of courage could overcome. German pilots, harried by fuel shortages, watched comrades forced to land or bail out not from combat damage but from empty tanks, and understood that the war was being lost not in the air but in the refineries and supply depots they could not protect. American pilots, by contrast, flew with a confidence born of material security. They knew that if they needed more power, it was there. If they needed to fly further, the fuel would be waiting. If they made it back to base, they would be refueled and airborne again within hours. That confidence, multiplied across thousands of sorties, became a strategic weapon as potent as any gun or bomb. The hidden war of chemistry, the story of 100-octane. Fuel is also a story of science outpacing expectation. The chemists and engineers who developed catalytic cracking processes were not thinking in terms of dogfights and bombing raids. They were thinking in terms of reaction temperatures, catalyst regeneration cycles, distillation curves. But their work, abstract and technical, translated directly into tactical advantages that commanders could exploit. Consider the physics. An internal combustion engine extracts energy by compressing a fuel-air mixture and igniting it. The higher the compression ratio, the more energy extracted per unit of fuel. But high compression generates high temperatures and pressures, which can cause the fuel to ignite prematurely before the piston reaches the optimal position. Knock wastes energy, damages the engine, and limits power output. Octane rating measures resistance to knock. A higher octane fuel allows higher compression without knock, which means more power from the same displacement, or the same power from a lighter, smaller engine. In practical terms, this meant that a Rolls-Royce Merlin engine, which might produce 1,000 horsepower on 87-octane fuel, could produce 1,300 horsepower or more on 100-octane fuel without mechanical modification. This was not a small improvement. It was the difference between a Spitfire that could climb to 30,000 feet in 10 minutes or 15. It was the difference between a P-51 that could escort bombers to the target and back, or one that had to turn back halfway. It was the difference between an F-6F Hellcat that could outrun and outclimb a Zero, or one that fought on even terms. The Japanese understood this. They attempted to develop their own high-octane fuel programs, but the technical challenges, combined with resource shortages and the relentless American submarine campaign that strangled oil imports from the Dutch East Indies, made it impossible. By 1944, Japanese aviation fuel production was collapsing. Pilots were sometimes forced to fly on fuel with octane ratings as low as 87 or even 80. Far below the 92-octane standard for which their engines were designed. The result was predictable. Engines that could not sustain full power, that knocked and overheated, that failed in combat when pilots most needed them. American intelligence officers, interrogating captured Japanese pilots, noted a recurring theme: the frustration and despair of flying. Aircraft that could not perform as designed because the fuel was not available. Germany fared somewhat better, but only somewhat. German synthetic fuel plants produced aviation gasoline in the 87 to 95 octane range. sufficient for most operations but inferior to Allied fuel. German engineers compensated with technologies like methanol water injection, which temporarily boosted performance by cooling the combustion process and suppressing knock. The BMW 801 radial engine in the FW190, for example, used MW50 injection to increase horsepower for short periods during combat. It was an ingenious solution, but it was also a band-aid over a fundamental deficiency. The system added weight, complexity, and required yet another consumable, methanol, that was in short supply. American pilots did not need such systems. They had 100-octane fuel. The epilogue of fire and reflection, the war ended in fire, in the ruins of cities and the silence of battlefields. In the summer of 1945, as atomic bombs fell on Hiroshima and Nagasaki and the world entered a new and terrifying era, the role of 100-octane fuel seemed almost quaint, a relic of a conflict that had been decided by technologies more dramatic and destructive. But that would be a misreading of history. The strategic bombing campaigns that devastated Germany and Japan, the campaigns that made invasion unnecessary or at least less costly, depended on air superiority. Air superiority depended on fighters that could escort bombers, that could sweep the skies of enemy aircraft, that could operate at altitudes and ranges that earlier generations of aircraft could not. And those fighters depended, in the most literal sense, on the fuel that burned in their engines. When the war ended, the United States had produced over 4.5 billion gallons of 100-octane aviation fuel. The refining infrastructure built between 1940 and 1945 represented an investment of over $700 million, more than $10 billion in modern terms, and employed tens of thousands of workers. That infrastructure did not vanish with peace. It became the foundation for the post-war aviation industry, for the jet age that followed, for the global economy built on air travel and air freight. The technical expertise developed during the war, the understanding of catalytic processes, of high-octane hydrocarbon chemistry, of large-scale production, logistics fed into civilian industries, into petrochemicals, into the suburban car culture of the 1950s and beyond. But the deeper legacy is symbolic. 100-octane fuel represented a choice made in the winter of 1940 to solve a problem that did not yet exist for a war that had not yet arrived. It represented the decision by engineers and executives to gamble millions of dollars on an uncertain outcome because the alternative, waiting, hoping, relying on inadequacy, was unthinkable. It represented the capacity of a democratic, capitalist society to mobilize its resources, not through coercion but through coordination, not through central planning but through the alignment of private interest and public necessity. The soldiers who flew on that fuel, the fighter pilots over Europe and the Pacific, the bomber crews on their long missions, the transport pilots who kept the supply lines open, did not think in these terms. They thought about the mission, about survival, about getting home. But they flew with the knowledge, conscious or not, that their nation had provided them with the best tools available, that no expense had been spared, that the fuel in their tanks was as good as human ingenuity could produce. That knowledge, that assurance, was itself a weapon in the decades since, as historians have dissected the war's turning points midway. Stalingrad, D-Day, the bulge. The story of fuel often goes untold. It lacks the drama of battle, the personal heroism of individual actions. It is a story of refineries and catalysts, of chemical reactions and production schedules. But it is also a story about what a society values, about what it is willing to invest in, about the invisible work that makes dramatic victories possible. There is a photograph, taken in 1945, of a P-51 Mustang sitting on a muddy airfield somewhere in Germany. The pilot is gone, the mission over. Fuel is dripping slowly from the wing tanks, pooling on the ground, a clear liquid catching the late afternoon light. It looks like water. It looks like nothing. But in that clear, volatile liquid was the distilled essence of industrial power, of scientific achievement, of a nation's commitment to victory. It was the fuel that powered the aircraft that won the war. And it began on a frozen morning in New Jersey, when a handful of engineers listened to an engine roar and knew they had changed the world. The skies are quiet now. The refineries still stand, repurposed or replaced, their towers still rising like monuments to a vanished urgency. The fuel they produce is different, cleaner, optimized for efficiency rather than raw power. But the lesson remains. War, in the end, is not only about the courage to fight. It is about the wisdom to prepare, the vision to anticipate, and the will to solve problems before they become crises. It is about understanding that the most important battles are often fought not on the field but in the laboratory, the factory, the refinery. And it is about recognizing that freedom, democracy, and survival sometimes depend on things as prosaic and as profound as a beaker of clear liquid burning in the cold winter air.